Hey, so for this video, we are going to start getting into hypothesis testing, and we're going to work on an activity that I would normally do in class, but I've tried to alter it a little bit so that we're able to do it here as instead. So you should have the packet that says activity t-distribution on it, and hopefully you've already watched the short video about William Gossett and go over those first three questions already. So I'm not going to go over those because if you watch the video, you already know the answer. And if you didn't watch the video, then go watch the video. Oh, you're right here. Go watch the video. Okay, so what we're going to do now is look at the second half, and you can play along with this. I left the webpage here. Or you could even just Google GeoGebra t-distribution on your phone or on your computer. And it has this little picture here, and we can look at different aspects of it. So I'm going to, let's see, I've never switched in the middle of a share. So let's switch over to my internet. Here we go. My Google Chrome. And so this is live right here. The other one was just a picture of the handout that you have. But what's going on is the red curve is our standard normal distribution, which another word for that is Z. So the red curve is the Z score. You can see at the bottom, following along with the red, we have 1, 2, 3 standard deviations out. And then once you get much beyond 3, it pretty much flattens out. Same thing on the left, -1, -2, -3. And so the red curve is Z. The blue curve is the T distribution. And this is what you just watched with William Gossett. And this is the table, the new table we've been using, but we haven't really gone too much into it, just started using it as a table. And you notice on the table, I talked about it before, how when n is small, all of those numbers are listed on the table. You could use the degrees of freedom of 1, 2, 3, all the way up to 30, 40 even, maybe on that table. And once you get beyond that, once you get a bigger degrees of freedom, a bigger sample size, then it starts jumping. And so the reason that is as the degrees of freedom increases, then the picture, the blue line gets very, 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 very close and actually turns into the red line. So when degrees of freedom is very small, this isn't wanting to play with me today. When the degrees of freedom is very small, we can see how they're quite separate from each other. The blue line is below the green line. I'm sorry, the red. The blue line is below the red line at 0, and the blue line is above the red line on the sides. But as we increase that degrees of freedom, the middle goes taller, the outsides go flatter, and the blue becomes the red. So kind of fun just to play with back and forth. Mine's not really working well. Oh, I just moved the whole slider. Okay, I think I'm done with that before I break the whole internet today. So let me jump back to where we were with the notes. And before we go on, I want to look at that table for a minute because we saw this, we just didn't talk about it per se on this table. So if you look at, I zoomed in too much. If you look at the bottom, the degrees of freedom, as we get bigger and bigger, where's my pen? Is my pen here? Nope, let me find my pen. That's what I get for jumping back and forth between technology. All right, there it is. As we get bigger and bigger, 100, 1,000, we end up leveling out at Z. So everything above 1,000 and above, that is all stuff that is unique to T. But this bottom line is saying that T and Z become the same once it's big enough. And really on that picture, it looked like once the degrees of freedom was 40, the pictures were pretty close together. And if you look at these numbers, I mean, once it's 1,000, look how close those numbers are together. In fact, they're the same. And then the other ones, they're pretty darn close. So that's what we're seeing on this picture or on this table. We will be using this table, and when it's time to do that, we will jump back over to this screen. But for right now, we were looking here. And just to summarize what I said was when the degrees of freedom is 40 and up, basically Z equals T. It doesn't matter, you know, they're interchangeable at that point. And so in other words, the T looks more normal or standard. Is that normal distribution? Whereas, that's a D, standard. Whereas between 0 and 40, there's quite a bit of difference in between them. All right, so here's the activity that we're going to do today. And so what I want you to do is look at this page here and just answer these 3 questions that are listed below. So before I go, I just want to explain this, what we're looking at. So this is the average feature film length from 1906 to 2013. On the y-axis, we have the length in minutes. And on the x-axis, we have the year that's being discussed. And so go ahead and look at the picture and then see if you can answer these 3 questions. All right, and we're back. And so going to this picture here, the first question said, using this graph, what year had the longest average movie length? Now, this graph is not perfect, and it's not like we can just isolate a specific year or specific time, but just in general, where do you think that average movie length is the longest? So from my point of view, it looks like around that looks like a little spike right there to be the highest number for the length of the movie. And even if you weren't quite sure what I was looking at, and maybe you looked up here at the top, I still think on the top of the blue or the top of the white fall in the same section. And so anywhere from maybe 1962 or 63 or 64, if you said any of those numbers, you're on the right track. It's hard to be specific with the details or lack of details we're given on this picture, but it looks like that is approximately something between 1960 and 1965. Okay, so in which decade or 10-year period would you say has the sharpest increase in average movie length? And so this, we're going to have all different kinds of answers because people will interpret those 2 things and then interpret that differently. So some people are going to look for the sharpest. And so we see this spike right here. We have that really sharpness. And so they'll say, okay, that was between 1910 and 1920. So that is a perfectly acceptable answer. 1910 and 1920. And then you would just say, why did you choose that? Maybe you say, because it had the sharpest spike in it. Or another answer might be, well, it said 10-year period. Now, typically we think of decades as starting with the numbers listed there, 1910, 1920, 1930, but really decade just means 10 years. So it doesn't necessarily have to start at a specific time. So you could even say, you know what, from this point to 10 years later, that was the sharpest increase. Or maybe you didn't think that. Maybe you said, oh, over here, maybe that was the sharpest. So whatever you answered for this question, so you could have said maybe 1915 to 1925, whichever one you picked, you know, just explain why you chose that. Because again, you're going to have different reasons depending on which answer you picked. So some people don't like this answer. I like this answer better. Some people don't like that one because it starts with has a 5 in the ones digit, so therefore they say it can't be a decade. you know, I've heard everything. It's fine. Keep it, whichever answer you like better, that's the one you should put. All right, finally, we want to answer which, from the graph, estimate the movie length of a movie in 2010. So 2010 is over here at the end. Following up, we want to estimate that time. And so I would say anywhere from, probably 85 to 88 minutes. If you had any of these answers, you're in the right ballpark, because again, it's hard to be specific. Minutes. But what I'm going to do is I'm going to choose 86 and call that the official answer, because we're going to need that answer for the rest of the problems. So if you said any of those numbers, you know, this is 80 right here, there's 90. So it's definitely right there in that middle. Then you're definitely in the right ballpark. It was just an estimate, but we're going to go with 86 as our official answer for this problem, because we're going to use it here in a minute to investigate. So going back to the top of this page, what we are trying to find out is, are movies getting longer right here? So this is definitely going to be a hypothesis test kind of question, because it's a yes or no question. And so yes or no questions are perfect for hypothesis tests, whereas when we had, we're not asking to find a number or estimate something, or estimate something. So in the last chapter, we're looking for a specific range for the mean, a specific range for the proportion, so we can estimate that. We're not looking for that in this section. That's the main difference between confidence intervals and hypothesis testing. Hypothesis testing is going to be a yes or no kind of answer. You're not going to be in that situation that you need to determine that. I'm not going to ever give you a list and say decide which is a hypothesis test and which is a confidence interval, but I wanted to point that out because you're looking at the beginning, not the beginning, but throughout this process, a lot of things are going to look familiar from chapter 8. Okay, so here's the question. We want to see if movies from 2018 had an average length longer than they did in 2010. So first we want to find our population characteristic of interest. So in this case, we're looking for mu, but in case you're unsure, think of what kind of thing that they're asking for. So anything that is quantitative is going to be mu. Is it a number? If it's a number, then you're going to answer, or the problem's going to be about mu. It's a question asking a number. So we're asking about the average length of movies. That would be answered in a specific number of minutes. So this is why we're using mu. For other questions in the future, if it's qualitative, then we're going to use P for proportion. So qualitative, so let me go back. This is our review from chapter 1 or 2. So this is numbers, quantitative is numbers, and qualitative is words. So what question are you asking? Are you asking a question about numbers? In this case, 86 minutes. So that would be a quantitative. That's why we're using mu. Or are you asking a yes or no question? I mentioned this in a previous video, but do you like Diet Coke? Yes or no? The answers are words. So therefore, that would be an example where we would use proportion to determine how many people like Diet Coke, something like that. So all these problems have numbers in them. So I'm not saying are there numbers in the problem. I'm just saying the question that's being posed, would it best be answered with a number with units? For example, 86 minutes, that would be mean. Or is it best answered with a a word, a yes or no, a black or white, up or down, anytime where you have those two words to answer. Okay, so this one we are using mu, and in this problem, mu is going to equal the true, or not need to be true, the mean length of movies in 2018 in minutes. If you can find the units, then you are using mean. If you cannot find the units, then you are using proportion. Okay, so now we want to figure out what are our competing hypotheses. And I say write it in symbolic notation. So we have our null and our alternative hypotheses. And if you have no idea what I just wrote, then you need to pause it right now and go watch the 9-1 video, because we went over this in detail in that. So if these symbols don't look familiar to you, go back and watch that. But here we are talking about mu. Our number is 86. And let's see, null is always equal. So to determine what the alternative would be, going to the question, oops, I skipped the question. We want to know if it is longer than that 86 minutes right there. So we want to know if it's greater than 86. So those are our competing hypotheses. It either equals 86 or it's greater than 86. So the claim is always going to be in the alternative, and then the equal sign is always going to be in the null. Okay, next up, significance level alpha. So just as a reminder, so this is from before, we talked briefly about alpha. If we had a 95% confidence interval, then that meant that if I subtracted it from 1, I would get, in this case, 0.05, which is alpha. Okay, so that's how alpha is related. 95% would be the confidence interval, which we would use in chapter 8, and 0.05 would be our alpha, which is what we're going to be using in chapter 9. So together, those two numbers equal 100%, or 1. Okay, so now for the new part, if no alpha is given, we're going to use alpha equals 0.05. 0.05 is a very common number to use for alpha, because that 95% is that middle, the middle two standard deviations to determine what's normal and what's not. So yeah, alpha of 0.05 is the most common. Now, some problems will say use alpha equal to 0.1, use alpha equal to 0.01. That's fine. If it gives it to you, use it. But if they don't tell you, then we're just going to default to alpha equals 0.05. All right, so this is a worksheet that I do in class that I mentioned earlier. So this part right here, we're going to skip, because normally I would break you up into groups and give you a list of 200 movies and give you a random number generator to make your own mean and all that good stuff and standard deviation. But I don't know how to do that. So what I did was I did it one time, and I put the numbers in my calculator, and so I'm just going to put those down here. So this is better also, because this way we'll all have the same numbers. Okay, so it says find the summary of stats using your sample technology. Just in case you come back to this later and you're like, how did we get those numbers? We're just going to say given by teacher, because I don't want you to look back later and not know where these numbers came from, but they literally are coming from thin air, because I did this part myself. I even thought about like, oh, I have you write down all the numbers and then put them in your calculator. And I was like, that's 10 minutes that we all don't need to be spending. So I did it, and these are the numbers I got. I got 95 for the mean, 32 for the sample size, 19.8 for the standard deviation, and 31 for the degrees of freedom. And again, this was my sample that I did of 31. I mean, you know it's a sample when it says sample size right here, so it has to be a sample. And so because it's a sample, I'm using my sample symbols. So X bar is mean, N is the sample size, and S is the standard deviation. Okay, so we're going to use those numbers down here on this next page. So what we want to do now is what test and distribution should we be using? So you already know the two tests, Z and T. And so now we just need to know which one is for which. And the good news is it's the same as confidence intervals. So we are going to use T for means and Z for proportions. That is not different than when you were finding the margin of error in confidence intervals. You would use the T for your critical value for means and the Z for your critical value for proportion. So it's that same association. So for this particular problem, we are going to use T because we are doing a problem with means. So since it's with means, we're going to use T. Okay, so what I did here was I wrote out both formulas, and since we decided we're using T, we are going to use this formula. This is a new formula, but it kind of looks like some other stuff that we did with central limit theorem, but with the mu in there. So this is new, but it just kind of looks similar to other stuff. And so we're going to plug in these numbers to find the test statistic. So the test statistic is something we are calculating. That's why I'm using the word calculate here. In a minute, we're going to find the critical value, and I didn't use the word calculate because we're going to look at a table. These are very key words to distinguish between. So when you get to the test and it says, what is the test statistic? You know I want you to calculate something. First is find the critical value. We're going to do that just like we did in chapter 8 and use the table. Okay, so for our test statistic, we are using all the numbers in this problem and going back to these numbers here. I have my X bar, I have my N and my S. So X bar is 95, S is 19.8, and N was the square root of 32. And so the only thing we need is mu. And for some reason, students have the hardest time finding mu, even though they literally wrote it out at the beginning of the problem. So when it asks for mu, or later on when it asks for P, when we do a proportion problem, just remember, you already figured that out. That was the first thing you did. So let's go back to the beginning. The first thing we did was we determined that mu was equal to 86 right here. We wrote that out. So we don't want to forget that we already did that. So then when we get to this problem right here, we say 86. All right, then you put it into your calculator. In terms of number of decimals, usually 2 or 3 is a good place to go. I don't want to round that too much. I don't want to round that to the number 3 and then really not have anything to compare. But nothing I do to explain this is really going to make sense right now until we get to the end. So we're just going to go with 2 decimal places, and then when we get to the picture in just a minute, it will hopefully make a little sense as to why we did that. Okay, so now we want to find the critical value, and this is from the table. So the test statistic, we used a formula, we calculated it. The critical value is from the table. And this is so important to know the difference because they both have the same name. Yeah, I didn't do it. Don't blame me. It's just what it is. And so the critical value is T because we're using the T table. And so I go to my T table, and now we're going to use it for the chapter 9 way. So remember down here at the bottom, the confidence interval, that was from chapter 8. And we are done with that. So we're going to go to the top, the part that we ignored before, and we are going to look at the area in 2 tails versus the area in 1 tail. And as I'm saying this, I realized we didn't talk about that yet. So let's go back to the notes real quick. And what we should have done, just like we did on that last worksheet, was say, okay, since mu is greater than 86, this is a right tail test. Okay, so right tail is just 1. So going here, it would, if it was 2-tailed, then it would be 2. But if it's right or left, then it's just 1. So I'm going to use this area in 1 tail number. And the numbers given here, the 0.25, the 0.2, all these numbers, you know, you read down on the chart for the degrees of freedom, that will give us our, or these are alphas. That's what I was trying to say. These are alphas. All those numbers on the list. So in this particular problem, we said that alpha was 0.05. And then we said the degrees of freedom was 30. Oh, I lost it already. Follow my line. 30 degrees of freedom was 31, but we're using 30 because that's the closest. So our critical value is 1.697. Okay, I'll write that down in a minute. But before I do, I wanted to point out these numbers you see here are all for, if I was using this area in 1 tail, this is all the right tail values. And it tells you right here, for left tail areas, use negative 1 tail values. So here, with my number, right tail, which is what we have, would be 1. This is getting sloppy. It would be 1.697. That's it. If this had been a left tail test, I would have used negative 1.697. So I still use the chart. I still scroll down to the right number of degrees of freedom. However, I just put a negative anytime it's left. And there's a few ways to help remember that. Obviously, the giant sentence at the top is a great way to help you remember that. But when we look at the picture that we're about to draw, then we will have another way. I'll show you. So let's just stop here since we just did this the other day. We are at a right tail test because it was greater than. So I'm going to draw a picture just like this on my paper. And so here I have, let's see, I'm going to skip ahead a little bit and then I will come back. Oh no, I don't have to skip ahead. It's right here. It is right tail. And we decided from our table that T equals 1.697. Now, don't draw this next picture because I'm about to erase it. But if this had been left tail, our picture would have looked like that. Remember, 0's in the middle. So if my picture was on the left, then it definitely needs to be a negative number because it is on the left side of 0. However, this picture is on the right side of 0, so it's definitely going to be a positive number. So that's another way that you can use to check to make sure you're using the right T value with a positive or negative. Okay, so this is what we're going to do now. So we're going to put all this together to make a decision whether we're going to reject or fail to reject the null hypothesis. So I haven't finished my picture, but I have my critical value. The line right here that I drew straight up and down, that is always the critical value. That's always going to be that line, is that number from the table. And what I want to do is I want to place my test statistic, 2.59, on this number line. So I see where 0 is. I see where 1.697 is. So 2.57 is somewhere over here. Doesn't have to be to scale. You just have to know, is it on the white side of the line or the blue side of the line? Because this side, whatever the tail is, that is our reject region. And so going back to our notes from the other day, we have on the right side, we're going to reject the null hypothesis, and all the green stuff over here was to fail to reject the null hypothesis. So anything to the right on a right tail test is the reject region. Anything to the left on a left tail test is the reject region. And then on the two tail test, we actually have on the right and the left, we have two reject regions. So that's what we're trying to do here, is we are trying to figure out where the line is, and the line comes from the critical value. And then where does our test statistic land? So now going back to the question of how do you know how many decimal places to round to? Well, it was fine to say 2.57. If I put 2.6, I would still know what side of the line that dot was on. But if this number had been if the numbers had been a little closer together, it would have been hard to compare if I truncated my number and I only wrote one decimal. So I try to have at least 3 different numbers, 3 different places on here. So I have the 2, the 5, and the 7, and that's usually enough to compare. I'm going to say this over and over again, it won't really seem that important. And then one day, and I think it's in chapter 12 or 13, there's a problem that if you round wrong, you'll get tricked. So my point is just have enough decimal places that you can compare. 2 is bigger than 1. Okay, I know that's enough to compare that my number is in the reject region. So what I'm going to do, according to my drawing, is I'm going to reject the null. We don't ever accept the null. We reject or we fail to reject. Those are the only 2 choices. You have the reject region and the fail to reject region. It's kind of like the difference between innocent and not guilty. So for example, O.J. Simpson was found not guilty. There was not enough information for them, or whatever happened in that trial, to find him guilty. But that doesn't mean that he didn't do it. It doesn't mean that he was innocent. It just means he's not guilty. So even though words sound the same sometimes, like fail to reject sounds like, well, if I'm not rejecting, I must be accepting. Nope, that doesn't work that way. We're not actually proving anything is true. We're just saying if it's bad or if there's not enough information to say it's bad. Okay, so since we are rejecting, we're going to write a conclusion for your hypothesis test. Just like chapter 8, all the conclusions are going to have the same kind of skeleton outline, and then you'll just fill in the blanks for the problem. This is the first time, so I'm going to write it all out, and I'm going to underline what's unique to this problem, but we will have lots of time to be practicing these problems over and over again. So there is sufficient evidence to support the claim. And then what we're going to do is, I'm writing this in red because I don't want you to literally write this, but we are going to write the alternative, because that is our claim. The claim is the alternative. So so don't actually write that you want to write the alternative. We're just going to actually write out the alternative. And our claim was that the average movie length in 2018 is longer than 86 minutes. Okay, there is sufficient evidence to support our claim, and then we write out the claim, which is the same as our alternative. You could have written greater than, that's fine, because that was, if you go back to the alternative, we said mu, the average, is greater than 86. Or if you go back to the question, it says longer than. So again, I don't care which words you use. But what's going to go on in the question is they're either, this is how you reject the null, is by rejecting the null, there's enough evidence to support the claim. And the claim is the alternative. So if you fail to reject, and we will get into that in another example in another video, if you fail to reject, then there is not sufficient evidence to support the claim. And then the claim itself will change with every problem. That's the alternative hypothesis. And just the alternative hypothesis in words. So we had that the average, which was mu, and what we're talking about, movie length, is longer than 86. So I just took our alternative and I wrote it out in words. Okay, there's a long way to go. This is the end of the problem. There's a long way to go. These problems are very long and they're tricky, but this was just the first one, kind of step by step. And I'm going to make 2 more videos about this topic. And by the third one, actually, I'm going to make 1 more that I want you to do with me. And by the third one, I want you to have done the worksheet and then watch the video after, because just to kind of check your work. Because this is a situation where like I would just kind of do all this on a Monday and kind of hurt your brains a little bit. And then 2 days later, I would kind of be working through it as you're kind of following along with me a little more. And then by the 3rd day, you would be hopefully working on this all by yourself or in groups. So we're going to try to mimic that as best we can over video. All right, well, I look forward to talking about hypothesis testing more, because it sounds like I have a few more videos to make. So I will talk to you later.